Our goal is to find a basis for this second-order differential equation, which I've written as Ly equals 0. So to start with this, let's assume that we can find some solutions to Ly equals 0, and let's say they're y1, y2. So all of that is fine. There could be more than 2, but we will stick with 2 for now. Okay. How can I have linearly independent functions? Right? What does that mean? So if I have some functions, let's say c1y1 of x, c2y2 of x, I'm curious about whether or not these things add up to 0. So linearly independent functions will have only the trivial solution to this equation. Right? If functions are linearly independent, they will have only the trivial solution to this equation. Trivial solution means the duh answer, and that means that C1 is 0 and C2 is 0. That's the only way to make them add up to 0. Now, if y1 and y2 solve your differential equation, that means you can differentiate them. And if you get this equation to work with, that means you can automatically differentiate both sides, and you can also consider this equation. And you can combine them together. You can consider both at once. C1y1 plus C2y2 of x is 0. C1y1 prime of x plus C2y2 prime of x is 0. You can write this in matrix form. y1 of x, y2 of x, y1 prime of x, y2 prime of x. That's being multiplied C1, C2 into 0, 0. These columns are going to be linearly independent if and only if the determinant of this matrix is not 0. If the determinant's not 0, the columns are independent. If the columns are independent, then the determinant is not 0. So it's a two-way street. Now, that also means if this determinant is non-zero, not only are you going to get those columns independent, it means you have the trivial solution to this problem. C1, C2 is 0, and that means that the functions y1 and y2 are independent. So to try to summarize all of that for you, I was asking about, well, what does it mean to have linearly independent functions? I need this combination right here to add up to 0 only if I take none of the first and none of the second. And it will turn out that a nice convenient test for doing that is related to this matrix. So here's a test. We will say that these functions y1 and y2 form a linearly independent set if and only if, so it's one way and the other, the determinant of this matrix is never 0 for any x. This thing is called the Wronskian. So not the matrix, but the determinant of the matrix. Now, as an example, at the beginning, we were talking about this differential equation, and I found two solutions. I found e to the 2t to be a solution and e to the minus t. Are these two solutions linearly independent? Sure. If I put them up here as y1 and y2, I can take their derivatives, 2e to the 2t, negative e to the negative t. And when I take the determinant, I'll get negative e to the t, subtract 2e to the negative t, or sorry, positive t. and I'll end up with negative 3 e to the t. Now, that will never be 0 for any t. And because they are never, the determinant is never 0, that means those two functions are linearly independent. That's good. Okay. So, if we have two solutions, basically we can use the Wronskian to check if they're independent. If we have two linearly independent solutions, I would now like to know, are they going to form a basis? There is one special result that is labeled as theorem 2.1.2 in our textbook and on the sheet. This is what's called the existence and uniqueness theorem for second order IVPs. Without this, we can't really come to the conclusions we need. There exists a unique, so unique means one. There exists a unique solution to this initial value problem. Our second order differential equation, which I'm going to write out explicitly here just so you remember, I of t naught is C1, y prime of t naught is C2. Second order equations need two initial conditions. They need something to do with the function and something to do with its second derivative, or its first derivative. Those two things in some way are independent because the dE itself will then impose a condition on y double prime. So if you state something about what the function and its derivative are doing at the beginning, then the equation itself tells you what the second derivative has to do. So you really only have freedom to talk about those two conditions there. By this theorem, 2.1.2, there must exist unique solutions to the following initial value problems. So I'm going to call this one IVP1. Ly is equal to 0. Y of t naught is 1. Y prime of t naught is 0. And we're going to call this solution y1 of t. We'll call this initial value problem 2. Ly of 0. Y of t naught is 0. Y prime of t naught is 1. And we're going to call that solution y2 of t. And then just some general initial value problem. So the general initial value problem, Ly equals 0, y of t naught is C1, y prime of t naught is C2. And we'll call this solution y of t. This and this initial value problem, these will guarantee a linearly independent set must exist. And how do they do that? Well, if I take those things, if I take the answers to those two problems and I dump them into the Wronskian, right? Remember, the Wronskian helps us check. If I dump them into the Wronskian, the nice thing about those initial value problems is that these initial conditions will guarantee that I will have a non-zero Wronskian, so they are linearly independent. y1 and y2 are linearly independent, so that's great. And now, now that I know that I have to have two linearly independent solutions, let's talk about taking a linear combination of those two, and then we're going to consider the general initial value problem. Okay. So by theorem 2.1.1, I know that C1y1 plus C2y2 is a solution to the differential equation itself, right? Any linear combination of solutions has to be a solution. If I were to take u at t naught, I will get C1y1 at t naught, C2y2 at t naught. That's going to give me C11 plus C20. That's going to give me C1. It has to be that. And then if I were to talk about the derivative of this, C1y1 prime at t naught, C2y2 prime at t naught, if I were to plug in the initial conditions for each of those things, I will get C2. So, by the existence and uniqueness theorem, that means that C1y1 plus C2y2 must be the unique solution to this initial value problem. The basis for Ly equals 0 is always these two linearly independent solutions. They're linearly independent, and then the general solution is always going to look like a linear combination of those two. Every answer will be formed from a linear combination of those two independent vectors. And another thing is that the second order dE has two basis functions. So in some way, the solution space is two-dimensional. Anything, any answer to any second order problem will always be formed from these two linearly independent functions. Now, just like in linear algebra, these bases are not unique. There are infinitely many bases, right? I and j are a basis, but so are 2i and 2j. Those form a basis for R2. But you can stretch those vectors. The same thing happens with functions. You can take y1 and y2, or double y1 and triple y2. They will still be linearly independent, but they're not unique. You can have infinitely many of them. So as long as you can find two independent functions, they are going to be guaranteed to be a basis. So we will talk about how to do it for that special case.